Hey, this is Daniel Rockwitz Reynolds with Christopher Nicolai, and I've been presenting recently on the concept of Computation Jockey CJ, which is an explanation that I've been having for DJ control interfaces like MIDI standard control devices, external audio interface boxes and units, and DJ devices like vinyl turntables and records. I presented at this at a 2016 Wolfram Tech Conference, kind of outlining the idea, and I also worked on it at the Wolfram Summer School 2017, and I also presented talks at the New School in New York City and Ithaca College Ed Tech Day 2016 for the general public and those in various communities such as artists, musicians, educators, mathematicians, scientists. And as an artist and musician and teacher by trade, I have been looking for a skilled computer programmer or team to possibly work with in order to communicate ideas and develop the idea in ways I cannot do alone at the present. And Christopher Nicolai here is famed in the community of Buffalo, New York for his computer skills and came highly recommended to me from many sources in various communities. He is a BA in computer science from Oberlin College and has worked at the SACS lab at SUNY Buffalo for the past 17 years. He is skilled in many computer languages: Display C, C++, CUDA, GL, SL, HTML, JavaScript, MIDI, Python, SQL, text, while also libraries such as DisplayBoost, NumPy, OpenCL, OpenGL, OpenMP, and remote sensors like real-time video input, cell phone sensors with GPS orientation, is interactive user input methods. And he runs a fractal art website called Mandelics.com. When meeting Christopher, I was impressed with how well we clicked, and that as I told him many long-standing problems I'd had for years, he was able to solve them in minutes to hours and longest sometimes days. And basically all these obstacles that I had had for years, he was able to implement them immediately using his background knowledge and all that, and his skills. So while many of that got solved, we'll talk about some of them. Number one was I'd been wanting to integrate multiple MIDI control pads easily to control visualizations with plug and play. Christopher wrote a JS GUI which can do just that.
So this is a Julia set. It's one of the famous original fractals that's related to the Mandelbrot set. And Dan here asked me if I could put a cellular automaton of his personal design on top of it. And I thought it looked like a neat idea. So what happens when you click here is that it seeds it at a point and then it spreads out a two-dimensional CA rule, one of the original 256, and it spreads it out in every direction. So you get a radial effect from a one-dimensional cellular automaton. This is rule 30. As it spreads out, you can recognize it in the down direction, but it's being rotated in every direction. Here's rule 37. Seems to get more interesting when it interacts with itself.
And so here we're showing we got the Chaos Pad KP3 Plus, and as we move the XY chord, it's sending in a MIDI signal, and that MIDI signal is being parsed here for the coordinates on the Julia set. We got like I and R and all that for the Julia seed. Down on the floor, we got a foot pedal, and when I step on the foot pedal, it'll like switch up the stuff. Well, this one don't have it saved. Okay. And you see here's a different one. It was saved, but I didn't realize. So this is one that was loaded up on a preset down there. Okay, and then we can launch the different CAs and all that with offsets as well and all this. So and a radial grid. And just keep changing the underlying Julia chords. Now, let's see. Jump to another preset. I had to press it harder. You see it's a little bit. This is the one that we were just on. It was already saved in the preset. That's what we got now. And when we save the presets, here's the we got the ability to see in here that it's like sending the MIDI stuff. So when you step in on the stuff, the MIDI presses down here, then you see that's the different buttons that you press with your foot. It's a little dark in here. Okay, so you step on those buttons, and up there it's showing you the different commands, and those can be mapped to presets or to activate stuff. And you also got foot controlled stuff like almost like it's like electric whammy pedal or something, where it's got like a different range that it sends. Probably a lot of times it's between 0 and 127, and all of these you can just plug and play basically, and also send in audio from audio sources, have that booming through there and all that, and DJ and stuff. So thanks Christopher for helping with that.
Okay. So these are your standard Julia set fractals. They're based off of a famous equation or iteration function really. You start with complex numbers, two-dimensional numbers, and you do z becomes z squared plus c. So to start off with, it's a simple function. If you have to compute it with basic high school algebra, you can do that, because each of these numbers, z and c, has a real part and an imaginary part, and the imaginary part is multiplied by I, and I squared is -1, and so you can square these things. What is maybe impossible to do with high school math is to take a complex number and put it to an arbitrary power. So that would be z to the p plus c, and right now the slider is set on the power of 2, so we're still seeing the standard fractal. But we were able to use a Wolfram Cloud API function to do the difficult math. It's actually going to be on this screen, to convert a complex piece of algebra like this into the high school algebra kind of style that's required for a graphics card. So this program's running on the graphics card, so we couldn't use nice facilities like Mathematica with imaginary numbers and complex numbers built in. We have to do everything in terms of real numbers and trigonometry and powers, basic functions that are built into all of the languages. So what we did is use a Wolfram Cloud API to convert it. So when you type in an expression like I did there, z to the p plus c, that gets sent to this Wolfram Cloud API. It's a fairly simple one. It takes in an expression and it puts out a string, or it takes in a string, it puts in a string actually. The string is named expression. So with a little bit of conversion to and from, the meat of it is this function complex expand. Now I've done that for example down here. to ask it to take z minus c to the 1 over this variable power, and expand it, assuming that z and c are complex, into its real and imaginary components. So this way, we'll take the two-dimensional, x-coordinate being the real and y-coordinate being the imaginary, and we can compute this on a graphics card using real arithmetic. And I would never have been able to derive this by hand, and I certainly wouldn't want to rederive it every time just to draw a new fractal, but that's, with the power of Mathematica, effectively what we can do here now. You could type in any expression you want. Now, I've typed in a few ahead of time. Some interesting ones are the convergence fractals, the Newton fractals, where you're looking at z being replaced by z minus a polynomial of z divided by the derivative of that polynomial. And in the general form, there is a factor that goes in front of that ratio. In this expression here, it's q. And this works better when you draw it in convergence mode. So we'll just have to locate an interesting set of exponents and coefficients here. Or else go back to my library of pre-chosen ones. No, that's a simple one. That's z to the minus 8 plus c. If we change the power here, we get different things. Now we can actually hook the power up to a MIDI slider. You're going to have to edit this a lot. We can actually hook the power up to a MIDI slider. So or a knob. So I'll spin this knob, and the screen, the control screen over here, the control window, is showing me that control change message channel 0 94 is changing when I turn that knob. So I'll click on it and assign it to the Z power. Now, as I turn it over here, you can see the slider moving. You can see the fractal changing. Now this slider right now is programmed for resolution, so I can make it as chunky or as high resolution as I want it. But I'm going to reprogram it now to run the Q factor in the expression that I've entered in. Oh no, got rid of the expression. Okay, reprogram it for the Q factor. Slider on resolution. Q. So this is maybe by itself not the most useful example of the awesome power of the Wolfram environment and Mathematica and cloud connections and everything. But the exciting part is that we have mathematical quantities such as P and Q that are literally at my fingertips, and when I turn this knob, when I move this slider, I can physically explore a mathematical space. You can imagine that if this was hooked in with a GIS system, you could change the expected amount of traffic moving through an intersection and watch what happens downstream in a traffic model. And it's nice having things at your fingertips and on a physical controller, because you have a lot of resources in your brain that are dedicated to remembering the physical position of things and to connecting those with other ideas. So it frees up my brain to do more useful things, and it frees up my time to do more useful things, and the display stays focused on the visualization rather than on the process of me mousing around and finding different things to show you. So I think that this, although it's a toy demonstration, would be very useful for real projects, especially if you didn't have to write a fancy JavaScript bridge just to get MIDI messages in. Because that's really the difference here, is that in addition to high-speed WebGL graphics, which hopefully would come at a future date, we're using musical instrument digital interface, MIDI messages, to control various parameters. MIDI is a very old-fashioned technology in today's terms. It communicates with single bytes, so most of the messages have a fairly limited resolution, like 0 to 127. There's the pitch bend message does have a 14-bit resolution, but it's a very fast protocol. It's basically similar to serial, and can communicate information along 16 or 15 channels. And that can be on the input direction or the output direction. So just like you have a knob or a sensor that's getting turned into a number and coming in via the MIDI cable in real time, you could have a quantity that's being computed from a model. You could have an index of air pollution, where the more pollution rises, the louder the obnoxious hissing sounds coming out of the computer sounds. So a planner who's using this model to track dozens or hundreds of different outcomes could be warned very specifically of what's happening with all of them, because our ears can distinguish dozens and hundreds of different frequencies and different things going on. You can go to an orchestra concert, and we can simplify and make the computer-human feedback loop more powerful with these kind of tactile and oral two-dimensional communication. This could be important with machine learning, because it's been shown recently that however fast you can train a machine on unsupervised data, supervised learning is quicker and more effective. And this would increase the number of different variables that could be supervised, and also the number of variables that could be ergonomically and quickly manipulated and responded to. So I think the most important thing to make this a reality, something that everyone can use Wolfram and mathematical tools to very quickly connect their existing MIDI equipment. If anyone has this, has a pedal board, has a keyboard that has a pitch bend wheel, these are all signals that are coming out of the MIDI cable, can be plugged into an existing computer, and with fairly simple software we can read these messages and produce them as Mathematica signals, or whatever the most appropriate mechanism turns out to be. What we're proposing is that this should be added to Mathematica as another one of the programmable APIs. We would model it after the gamepad API in particular, because a lot of signals are coming in a similar fashion. They're on an axis that's digital or analog. And we would also look at the audio APIs when designing that. I've done quite a bit of work with the Java native interface, and also with programming MIDI in C. So I don't think there would be a great technical challenge. Certainly Google has done it with Chrome. Every version of Chrome, whether it's on Android or Linux or Mac OS or Windows, possibly not on iOS, but in general any version of Chrome taps into the system MIDI facilities and presents a consistent MIDI API. That's how I was able to read these messages in. So I think we could do the same thing for Wolfram and dramatically expand the feedback loop between abstract math programs, or physically inspired or physics inspired data-driven programs, and link up with existing hardware to make it more effective. I mean, I can't quite picture a commissioner of planning up at the podium talking about their different options for configuring the number of lanes, and holding an Xbox controller and switching between option A, B, C, D. But I could more readily picture them using a MIDI knob board such as this. This would fit unobtrusively on the podium, but it would still look good in photo ops. It would look very professional, and I think that they would have no hesitation in looking like the wizard of the presentation, thanks to physical controls that you don't have to be worried about messing with the screen or learning an interface for. Your tech assistant can tell you just move knob B and you'll be set.
My needle's almost like broke, but you can still see, just if you want to get the demo out, that even with the needle kind of messed up, you can still see that as I'm scratching, it's changing the picture on there. So I'm scratching with the DJ stuff, and it's changing the picture up there. So, and we got the different chords we're using, so a lot of the MIDI stuff, and it's pretty cool. So thank you very much, and we hope this could be like some sort of project or something. So just keep it up with Computation and keep it cool.